All right, today we're going to unlock one of the most powerful tools in your entire algebra toolkit, function composition. We're going to see what happens when we take the functions you already know and combine them in a new and honestly a really cool way.
So, you've already gotten comfortable with adding, subtracting, maybe even multiplying functions. But what if we could go a step further? What if we could take the answer from one function and just plug it straight in as the start of another one, creating a kind of mathematical chain reaction? Well, that's exactly what we're about to do. Here's our game plan. First, we'll cover what composition even is. Then we'll decode that funny-looking notation. We'll see it in action with some real examples. I'll show you the common traps to avoid. And finally, we'll talk about why this whole thing actually matters.
Okay, let's dive right in. First things first, what in the world is function composition?
At its very heart, it's all about this idea of feeding one function into another. You take the entire result from your first function, and boom, it becomes the starting number for the next one. Think of it like a seamless handoff.
You know, the best way to visualize this is as a machine pipeline. Seriously, imagine an assembly line. The first machine spits out a part, and that part immediately gets fed into the second machine for the next step. That's function composition, right there.
Now, like any new concept in math, composition has its own unique language. So let's break down how to read and write it, because once you see it, you'll realize it's not intimidating at all. So you're going to see this notation, an F, then a little open circle, a G, all in parentheses with an X. That little circle, all it means is composed with. So we just read the whole thing out loud as f of g of x. That's it.
So what does f of g of x actually tell us to do? Well, it translates to this, f of g of x, where the g of x is literally nested inside the f function. And this right here, this gives us our golden rule. You have to work from the inside out. Always solve the inner function first. This brings us right back to our pipeline. Your starting value x gets plugged into the inner function g. It churns for a second and spits out an answer, g of x. That answer then immediately becomes the input for the outer function f, which gives you your final result. All right, enough theory, right? The best way to get this is to actually see it work. So let's walk through two really solid examples.
Okay, for our first example, we've got two functions. F of x equals 2x plus 3 and g of x equals x squared. Our job is to find f of g of 4. And notice, this time we have a specific number, 4, to start with.
Okay, what's the rule? Inside out. So the first thing we do is solve the inner function g of 4. We plug 4 into g of x, which is just 4 squared. That gives us 16. Now, that output, 16, becomes the input for our outer function f. So we calculate f of 16. That's 2 times 16 plus 3, which gets us to 35.
And there it is, the final result at the end of our pipeline. F of g of 4 is 35. Simple as that.
Great. Now let's level up just a little bit. We're going to use the exact same two functions, but this time we're going to find the general formulas for both f of g of x and g of f of x. And this is going to show us something really important.
So check this out. For f of g of x, we take the entire g function x squared and substitute it into f. That gives us 2 times x squared plus 3. But when we reverse it for g of f of x, we take 2x plus 3 and substitute that into g. That gives us the whole quantity of 2x plus 3 squared, which is a totally different formula. The takeaway here is huge. Unlike regular multiplication, in function composition, the order you do it in matters a lot.
You know, knowing the rules is great, but knowing the common traps is even better. Let's look at the two biggest mistakes students make so you can just sidestep them completely.
Hands down, the number one mistake is getting the order backward. When you see f of g of x, even though g is written on the right, it is the inner function. It's the first machine in the pipeline. It always runs first. Don't let your brain's habit of reading left to right trick you here.
And the second major trap is confusing composition with multiplication. I get it, that little circle looks a bit like a multiplication dot, but it is not. Composition is an act of substitution. You are replacing the variable in one function with the entirety of another function. It's a completely different idea from multiplication.
So why are we even learning this? Is it just some abstract mental exercise for mathematicians? Absolutely not. Let's connect this to the real world and to where you're headed next in math.
Think about shopping. Let's say a store is offering 20% off an item, but you also have a $10 off coupon. The final price you pay is literally a composition of functions. And think about it, does it matter which one you apply first, the percentage off, or the flat $10 off? Oh yeah, it absolutely does. That's composition right there in real life.
And looking ahead, this isn't just some one-off topic we're going to learn and forget about. Understanding composition is the absolute key to unlocking the next big concept in algebra, inverse functions. You're going to use this exact skill to prove that two functions are inverses of each other. It is a critical building block.
So you've just mastered a really sophisticated new way to combine functions, building these mathematical pipelines where you know that order is everything. So the only question left is, are you ready to take this brand new skill and use it to find a function's inverse?